here is what I need to evaluate in that experiment, right? Here's the data that I need to accumulate while doing that experiment. So, in order to compute that, what I will need for this tau steps, I will need to record every state, so where I was and my turning angles, and the velocities, the angular velocity and translational velocity of everything. Protocol, run episode number 1, number 2, number 30. Okay? For each of this, okay, I do just sum up and calculate all rewards. So I know how to calculate the function for each state connections. Then I will just divide by the number, right, of episodes. Just of this. So I just stresses the episode. That's what you do. Now, this thing here is an instruction on how to do the experiment. That's an instruction. You're not doing some random experiment, right? You're running this robot. And that robot evolves, in your context, evolves according to its dedicated state transition law. Now, final thing. The way you decide what actions to take is summarized in the concept called policy. We denote pi. So pi is the policy. So now you get another confusing word besides environment, reward, policy. I don't know what robot is doing policy, but okay, maybe I'm just too narrow-sighted. But anyway, that's the way it is. So policy, and the reason why I use capital letter here is because specifically in many reinforcement learning algorithms, many policy grading algorithms, some actions have to be taken with a certain degree of randomness. It's for so-called exploration, but we will get to it later. So, pi is a PDF. Another PDF. So, A, T is sampled from pi. And the only variable that PDF depends on is just the current state. We decide what to do depending on what state we are at. Okay? So, these things, we will have a lot of them. I encourage you, if you don't like my interpretation, just, ignore it. If you use yours, come on. If you like, whatever, you can think of this as such. Because that, especially in policy gradient theory, we will have to unroll it, or roll it up and decipher it. And that would be, like an integral, but eventually, like integral or sum, it will have a very concrete and definite computational procedure behind it. We try to keep everything, whatever the mathematical concept we use, everything will have some computation on it. Not only computation, but also, as I described, experimental. So, to summarize, reinforcement current mostly deals with Markov chains in discrete time, in continuous state space, and discrete, not necessarily just discrete or finite, but mostly discrete time. Okay? The central object is a Markov chain whose evolution has the property that each subsequent state depends on the state connection. Our problem is to maximize, in general, maximize accumulated, that means accumulation. Reward, specifically certain statistic thereof, most of them is just the mean expected value, whereby the decision variable is the policy. Then there's also discount factor that we didn't talk yet about, but we will. That, like compared to ML, it's classical ML, the sheer existence of that underlying Markov chain that environment is like a Pandora box. Okay, so we'll wrap up here. Any questions? Please use the time here to try to avoid common. Don't get me wrong, but please ask questions during the class. When I ask you, do you have questions? Please ask them. Okay, just a second. Don't try to catch up with me during the break. I also need some break. I also need to chill out, after the lecture. Ask here or ask on the chat, if you don't mind.
Okay, on the slide, when there was like some ST plus 1 was generated from n FTST to GTAT. But is there okay, because we have matrix 3x3 and 2x2, how can we sum them up if you have vectors of
yes, your question is correct. Probably the G matrix should have, there was probably a missing, row.
Okay.
Yeah. It's a good one. If possible, please write this remark also in the general chat. It's probably, you know what I mean, right? You just oil or discretize. That is 3 by 3, then there's 3 by 1, plus it should be 3 by 2, 3 by 2, 2 by 1. So it was your action acts like the V's you have on the X, Y, and the angular acts on the third state, which is, it's a good one.